Welcome to the API 571 Audio Masterclass series. This episode is brought to you by Mag Integrity for the complete high-resolution study guides, API 571 exam prep question banks, and to unlock our full private audio library, visit our premium engineering portal at magintegrity.ca.
Glad to be here and ready to get into it.
Yeah, absolutely. So imagine doubling the concentration of a highly corrosive chemical in your refinery's process stream.
Right, you'd think that'd be a disaster.
Exactly, but the data tells you that your piping is actually safer because of it. Or, consider finding out that the heavy, continuous welds joining your massive pressure vessels are completely sound, but a tiny, seemingly insignificant bracket welded onto the outside of a pipe decades ago is about to cause a catastrophic rupture.
Yeah, it's wild. It completely defies common sense.
It really does. So today we're dismantling the intuition behind one of the most stealthy and, frankly, misunderstood damage mechanisms in the hydrocarbon processing industry. Our mission for you today is a highly detailed, zero-fluff technical briefing focused entirely on Section 3.3 of API Recommended Practice 571.
Which is, of course, Amine Stress Corrosion Cracking, or Amine SCC.
Right, and we really need to establish the baseline immediately here. We are not talking about general corrosion, uniform thinning, or, just obvious rusting.
Oh, far from it. I mean,
No.
general corrosion is, it's a predictable adversary, right?
Yeah.
It consumes metal uniformly.
You can just track it with standard ultrasonic thickness readings.
Exactly. You plot a corrosion rate, calculate a retirement date with, well, a reasonable degree of engineering certainty. But Amine SCC operates on an entirely different metallurgical plane.
Because it leaves the bulk thickness totally untouched, doesn't it?
It does. You could have a section of carbon steel pipe that mics out perfectly to its nominal wall thickness. It looks immaculate from a macro perspective.
But microscopically.
Microscopically, the grain boundaries are being systematically unzipped from the inside out. We're hunting a mechanism that relies on the convergence of mechanical stress, localized metallurgy, and specific environmental triggers.
And it leaves basically zero visual evidence until the exact moment of failure, which makes this a terrifying mechanism for an inspector.
Oh, absolutely. You can't just walk out and look for a thin spot.
Right, so we need to understand the exact physics of where this initiates. Reviewing the text of Section 3.3, there's this immediate paradox regarding the geographical location of these cracks.
The whole where is the crack actually forming debate.
Yeah, because when an engineer considers a weld as a failure point, the automatic assumption is that the weld metal itself, the filler metal that was melted and deposited, is the weakest link.
Or maybe the immediate heat-affected zone, the HAZ, right there at the fusion line.
Exactly. But the API text explicitly notes that these process-side surface cracks most often spawn in what it defines as the high residual stress zone. And that zone isn't in the weld.
No, it's adjacent to it. It's a critical distinction. It forces us to look at the thermodynamics of welding rather than just the chemistry of the metal.
Okay, so break that down for us. What is the mechanical reality of creating a weld?
Well, think about it. You're introducing a localized heat source approaching, like 3,000 degrees Fahrenheit to melt the steel.
That's a lot of heat.
Right. And that liquid metal pool expands, but it's surrounded by a massive heat sink, the cold, unyielding base metal of the pipe or the vessel.
So what happens when it cools?
As that weld pool rapidly cools and solidifies, it desperately attempts to contract. However, the surrounding cold steel acts like an immovable vice. It prevents that natural thermal contraction.
Ah, so instead of shrinking, the weld metal and the immediate surrounding base metal are subjected to this immense permanent tension.
Exactly. They are locked in tension.
I always like to visualize it like a sheet of tempered glass. To the naked eye, it looks perfectly stable, totally inert.
That's a great analogy, actually.
Right. But structurally, it's a battlefield of locked-in tensile forces, just waiting for the slightest microscopic disruption to violently release that energy. The steel in that specific zone is stretched to its absolute atomic limit.
That is a highly accurate way to model it. And the text defines the location of this maximum tensile stress, the high residual stress zone, very precisely.
Where exactly is it?
It typically manifests beyond the metallurgical heat-affected zone. We're looking at a localized band of material located approximately a tenth of an inch away from the actual weld toe.
A tenth of an inch, or I guess several millimeters for the metric crowd.
Yeah, just a few millimeters. But that specific physical distance represents the absolute peak of the stress tensor. The atomic lattice in that band is heavily distorted.
And that distortion represents stored potential energy.
Exactly. So when you introduce a specific chemical agent, in this case the amine solution, That agent doesn't even need to do all the work of breaking the atomic
But
bonds.
because the mechanical stress has already brought those bonds to the brink of failure.
You nailed it. The amine simply acts as the catalyst to push them over the edge.
So, as an inspector or an asset integrity engineer, you aren't just scrutinizing the weld cap, you really have to interrogate that invisible borderland a tenth of an inch away.
Right. You have to know exactly where to look.
But a crack is just a linear indication on an NDT report until you actually prove what caused it, right? I mean, other mechanisms like wet H2S damage or thermal fatigue can produce cracking near welds, too.
They absolutely can. Which is why the text mandates metallographic confirmation for a positive diagnosis of Amine SCC.
Okay, so what is the exact microscopic fingerprint we're looking for when we put a core sample under the lens?
Well, you have to look at the crystallographic structure. The text outlines 3 mandatory characteristics for positive identification.
And what's the first one?
First, the cracking is predominantly intergranular. Second, the crack network is oxide-filled.
Okay, intergranular and oxide-filled. And the third?
Third, the cracking morphology exhibits branching. If you don't have that specific triad of characteristics, you cannot definitively classify the failure as Amine SCC.
Okay, let's unpack the physics of that triad, starting with the intergranular nature. We know that steel is a crystalline lattice, and those crystals form grains.
Right. And the boundaries where those grains meet are inherently mismatched.
Because the atomic spacing is irregular compared to the perfect lattice inside the grain itself, right?
Exactly. The grain boundaries are regions of high energy and slight atomic disarray. Because of this structural mismatch, they become the paths of least resistance for chemical attack.
As opposed to transgranular cracking.
Yeah, transgranular cracking, where a crack shears straight through the atomic lattice of the grain itself. That requires massive amounts of mechanical force or a different type of environmental embrittlement.
But with Amine SCC, that localized tensile stress we discussed earlier just concentrates at these mismatched grain boundaries.
Exactly. The alkaline solution infiltrates these high-energy pathways, effectively dissolving the metallic bonds between the grains.
So it basically snakes its way through the microscopic mortar of the steel rather than breaking the bricks.
That's exactly how it works.
Yeah.
And as it snakes through those boundaries, it leaves behind a specific residue. Which brings us to the second characteristic.
The cracks are oxide-filled.
Right. And this isn't just a harmless byproduct. It's an active participant in the destruction.
Because when the exposed grain boundary reacts with the environment and forms iron oxides, we have to consider the Pilling-Bedworth ratio, don't we?
We absolutely do. That's a crucial thermodynamic concept here. The volume of the iron oxide molecule produced is significantly larger than the volume of the base iron atom it replaced.
Which creates an insidious mechanical phenomenon known as the wedge effect.
Precisely. As the crack opens up the grain boundary, the oxide forms inside the microscopic void. Because the oxide requires more physical space, it acts like a microscopic crowbar.
Exerting immense localized physical pressure against the crack walls.
Yeah, it's essentially manufacturing its own mechanical stress.
That's crazy. You have the residual stress from the welding pulling the crack open, and now you have the physical bulk of the oxide wedging it further apart from the inside.
Right, which increases the local stress intensity factor at the crack tip. That exposes fresh grain boundary, which then oxidizes, creating more volume, driving the wedge deeper.
It's just a terrifying self-feeding loop of structural degradation.
It is. It's a continuous autocatalytic cycle. And because of this reliance on the grain boundary network, we see the third characteristic branching.
How does the branching actually happen?
Well, as the localized stress field at the crack tip pushes forward, it eventually encounters junctions where multiple grains meet.
And the crack has to decide which way to go.
Exactly. It will naturally follow the path of maximum tensile stress and maximum atomic mismatch. This rarely results in a single straight fissure.
Instead, it bifurcates.
Yeah, it splits off into multiple directions following the chaotic topography of the grain boundaries.
I imagine under a metallographic microscope, it looks almost like a dendritic structure, like the root system of a tree.
Or a microscopic lightning strike permanently etched right into the steel. So if a metallurgist sees an intergranular branching oxide-filled figure sitting a tenth of an inch from a weld toe.
The diagnosis is confirmed. Amine SCC.
Exactly right.
Okay, so we've defined the precise nature of the failure and the microscopic weapon used. Now we really need to address the susceptibility of the materials.
Material selection is everything here.
Section 3.3 identifies the primary material at risk. It's carbon steel. but it makes a very specific metallurgical distinction. It explicitly calls out carbon steel that is non-PWHTD.
Right, meaning it has not undergone post-weld heat treatment. That is the definitive material parameter for this mechanism.
So the absence of post-weld heat treatment is what transforms a standard piece of industrial carbon steel into a highly susceptible target.
Absolutely. As we established, stress corrosion cracking is a synergistic mechanism. It requires three concurrent factors.
Susceptible material, aggressive environment, and high tensile stress.
You got it. The carbon steel provides the susceptible grain boundaries. The amine provides the environment. But it's the lack of PWHT that provides the critical threshold of tensile stress.
Let's look at the alternatives provided by the API text. Because if non-PWHT'd carbon steel is fundamentally vulnerable, there are going to be times when engineering requires a total bypass of that risk.
Sure, when you just can't risk it.
The text lists solid or clad stainless steel or other corrosion-resistant alloys, commonly known as CRAs. Why does changing the alloy completely shut down this specific cracking mechanism?
It really comes down to the fundamental crystallographic structure of the alloy. Carbon steel, at ambient operational temperatures, typically features a body-centered cubic or BCC atomic lattice structure.
Specifically, a ferritic or pearlitic microstructure, right?
Correct. And this specific atomic arrangement, combined with its grain boundary chemistry, is highly vulnerable to the localized anodic dissolution caused by the amine.
But when we upgrade to the 300 series stainless steels, the austenitic stainless steels, we're dealing with a completely different crystal lattice.
Right, we move to the face-centered cubic or FCC structure.
And why is FCC better here?
The austenitic FCC lattice has more slip planes. It's inherently more ductile at a microscopic level, which allows it to distribute localized stresses much more effectively than the rigid BCC structure of carbon steel.
Oh, that makes sense. It basically absorbs the stress better.
Yeah, exactly. Furthermore, austenitic stainless steels form a highly stable, continuous, and impermeable chromium oxide passive layer on their surface.
And that passive layer holds up against the amine.
Incredibly well. It's incredibly resilient in ebonine environments. The amine simply cannot initiate the localized dissolution required to attack the grain boundaries.
So the thermodynamic driving force for the crack initiation is just neutralized.
Completely neutralized.
Now, the text specifically mentions clad stainless steel as an option too, which is a critical economic and engineering reality.
Oh, for sure. You rarely see a massive, high-pressure amine regenerator tower built out of solid 316L stainless steel.
The cost would be astronomical.
Astronomical. And solid stainless doesn't always provide the heavy structural tensile strength required for massive pressure vessels anyway.
That's where roll-bonded or explosively bonded cladding or weld overlay becomes the engineering solution.
Exactly. You utilize heavy, thick-walled carbon steel for the pressure boundary, the structural skeleton of the vessel.
But you apply a thin, continuous layer of austenitic stainless steel to the internal, process-facing surface.
Right. And as long as that clad layer remains intact, acting as an impermeable crystallographic shield, the aggressive amine never touches the susceptible, stressed carbon steel beneath it.
So the mechanism is defeated by physical isolation.
Defeated before it even starts.
Okay, so we understand the metallurgy and the material limits, but if we must use carbon steel, and refineries have miles and miles of carbon steel piping in a pyramine service, we have to understand how the process fluids interact with that steel.
Right, the operational variables.
Exactly. And this brings us to Section 3, critical operational variables and drivers. And this is where the API text dismantles a very common engineering assumption regarding chemical concentration.
The concentration myth.
Yes, because if you're dealing with a corrosive acid, common sense dictates that a higher concentration equals more aggressive attack. A 5% acid solution might pit a pipe, but a 50% solution will eat through it in days.
That's what your gut tells you.
Yet, Section 3.3 explicitly states that amine concentration does not behave this way.
It's a totally counterintuitive reality of this specific damage mechanism. The text clearly states, amine concentration does not appear to have a significant effect on the propensity for cracking.
Which is wild. It forces operators to abandon the assumption that diluting the amine makes the system safer.
Right. You can push the concentration of DEA or MDEA higher, and it does not linearly increase the risk of grain boundary attack.
So if it's not the gross percentage of amine in the water, what is the primary driver?
The primary driver is the chemical state of the amine solution.
A chemical state. And the text draws a massive dividing line between two distinct operational states. lean amine and rich amine.
Yes, lean versus rich.
Now, for an engineer outside of a gas treating unit, rich sounds decadent and heavily saturated, therefore more dangerous, and lean sounds stripped down, clean, and safe.
But the chemical kinetics dictate the exact opposite for stress corrosion cracking.
Okay, walk us through that. Why is lean worse?
Well, you have to look at the purpose of the amine. Its thermodynamic role in the refinery is to absorb acid gases, primarily hydrogen sulfide, H2S, and carbon dioxide, CO2 from hydrocarbon streams.
So when the amine is lean, what does that actually mean?
It means it has just emerged from the regenerator, it has been boiled, the acid gases have been stripped out of it, and it is chemically hungry. It has a high affinity to react and absorb.
And when this hot, hungry lean amine contacts the stressed grain boundaries of carbon steel,
It aggressively facilitates the localized anodic dissolution we discussed earlier. It attacks.
but once that lean amine contacts the sour hydrocarbon gas, it absorbs the H2S and CO2, becomes rich amine.
Yes, it is chemically saturated.
And the API text states that equipment in rich amine service is actually less susceptible to cracking than equipment in lean amine service, which is crazy. Why does loading the fluid with highly corrosive acid gases actually protect the carbon steel from this specific cracking mechanism?
It's all about the formation of a protective surface scale.
Scale?
Yeah. When the amine becomes rich with H2S, that hydrogen sulfide reacts with the carbon steel surface to form an iron sulfide, or FeS, layer.
Now, in many other contexts, iron sulfide scaling is a huge problem.
Oh, it's a nightmare in other units.
Yeah.
But in the specific context of Amine SCC, that continuous, tightly adherent FeS layer actually acts as a barrier.
It passivates the steel surface.
Precisely. It physically blocks the amine from accessing and dissolving those highly stressed grain boundaries. The saturation of the fluid effectively seals off the initiation sites.
So lean amine is dangerous because it's aggressive and the steel is bare. Rich amine is safer because it builds its own protective shield on the steel.
Exactly. But, and this is a big but, the text does not give rich amine a total free pass.
Right. It explicitly states that rich amine systems are less susceptible, but it outlines critical exceptions. There are specific vulnerability zones, even in the rich amine loop.
Yes, and these vulnerability zones exist wherever the thermodynamic equilibrium of the fluid is disrupted.
The highest risks in rich systems occur specifically in vessels where the chemical state is actively changing, right? Where the acid gas is either entering the amine or leaving the amine.
Phase transitions.
Exactly.
When you're absorbing gas, or more importantly, when you're stripping the gas out of the rich amine, the fluid is extremely turbulent. You have flashing, boiling, and the rapid desorption of H2S and CO2.
What does that turbulence do to our protective scale?
This dynamic chemical shifting, combined with the thermal and mechanical turbulence, destabilizes and literally strips away that protective iron sulfide scale.
So the barrier is constantly being broken down and rebuilt.
Exactly. And during the periods where the FeSing scale is stripped away, the highly stressed carbon steel is suddenly exposed to a fluid that is rapidly becoming lean and aggressive.
Because the gas is leaving it.
Right. And that transient exposure is all the mechanism needs to initiate a crack.
Wow. Which perfectly transitions us into mapping the actual refinery. Because if I'm an inspector out there, I need to know exactly which vessels and which specific piping circuits are subjected to these dynamic phase transitions.
You need a map.
Exactly. And Section 4 provides a meticulous hit list of affected equipment. Let's walk through the amine loop and identify the thermomechanical stressors in each piece of equipment. The text lists contactors, absorbers, strippers, filters, regenerators, and heat exchangers.
It's essentially the entire gas treating unit, but we should break down why each is vulnerable.
Let's start with the front line, contactors and absorbers.
Right, the contactors and absorbers are where the lean amine first contacts the sour gas. So you have the chemical transition from lean to rich occurring right there across the fractionator trays or packing.
And you have thermal gradients plus massive pressure boundaries.
Exactly. If those vessels are constructed of non-PWHT'd carbon steel, the welds supporting the trays and the main seam welds are at very high risk.
Okay, then the rich amine moves to the regenerator and stripper section.
And this is arguably the most severe environment. The regenerator uses high heat to boil the rich amine, forcing it to release the absorbed H2S and CO2.
So you have the worst possible combination here.
You really do. You have high temperatures, which increase the kinetic energy of the corrosion reactions. You have dynamic phase transitions as the gas flashes off, which strips the protective FeS scale.
And the bulk fluid is aggressively returning to its highly reactive lean state.
It's a perfect storm.
The text also includes filters in that list, Which is interesting because filters are usually viewed as passive, low-risk components.
Yeah, they often get overlooked, but they're subjected to continuous flow, often handling the lean amine right after it has been regenerated.
Right. And the differential pressure across the filter housing, combined with the aggressive nature of the lean fluid, creates a high risk for any non-stress relieved welds on the housing body or the inlet-outlet nozzles.
Exactly. And then the text adds a critical sort of catch-all operational warning that extends the risk far beyond the physical boundaries of the amine unit itself.
Yes, it states that any equipment subject to amine carryover is vulnerable. This feels like the most insidious part of this mechanism.
It really is because it catches people off guard. Amine carryover usually occurs due to foaming in the contactor.
If the amine solution becomes contaminated with liquid hydrocarbons or fine particulates, it foams up, much like a pot boiling over on a stove.
Yeah, and that amine foam gets swept up into the overhead vapor stream and carried downstream into process units that were simply never designed to handle amine.
So you might have a downstream fuel gas piping circuit or a section of the hydroprocessing unit made of standard non-PWHT'd carbon steel.
Right, because the design engineers never intended for that pipe to see amine, so they didn't mandate the expensive heat treatment during fabrication.
But suddenly, due to an upstream foaming upset, hot amine is introduced into that piping.
And boom, the stressed welds in that downstream system are now exposed to the exact environment required to initiate Amine SCC.
It really forces inspectors to track the actual flow of process upsets, not just the intended flow lines on a piping and instrumentation diagram.
You have to think outside the normal operating window.
Now, regarding the specific morphology of the failures in this equipment, the text provides a highly detailed visual hallmark found in heat exchangers. It highlights radial amine SCC cracks emanating directly from the bore of a nozzle in rich amine reboiler exchangers.
Radial cracking. Yeah, let's dissect the stress tensors at play here. Because a nozzle isn't just a hole in a pipe, it is a massive structural discontinuity.
It's one of the most complex stress concentration zones in any pressure vessel, isn't it?
Without a doubt. When you cut a circular hole into the thick shell of a heat exchanger and weld a cylindrical pipe into it to form a nozzle, you completely disrupt the continuous distribution of pressure-induced stresses.
Because the internal pressure of the vessel creates hoop stress, the force trying to burst the cylinder open and longitudinal stress.
Right, and at the exact edge of that bore, the hoop stress is magnified significantly, often by a factor of 2 or 3 compared to the nominal shell wall.
And because it's a reboiler exchanger, we have to layer on thermal stress, too.
Exactly. The shell might be thick and massive, taking a long time to heat up, while the thin-walled nozzle pipe heats up very rapidly as the hot fluid flows through it.
So that differential thermal expansion between the thin nozzle and the thick shell creates immense localized bending stresses at the weld junction.
It does. So at the bore of that nozzle, you have triaxial stress concentrations, magnified hoop stress, longitudinal stress, and massive thermal gradients.
And cracks will always propagate perpendicular to the maximum principal stress, right?
Always. Because the hoop stress attempting to pull the bore open is so high, the cracks initiate at the edge of the hole and propagate outward into the shell plate.
Which creates a starburst pattern, or radial cracking, emanating outward from the center of the nozzle bore.
Yep, a starburst. And you combine that extreme mechanical stress state with the boiling, phase-transitioning rich amine inside the reboiler.
You have the perfect storm for rapid, localized failure.
It's a textbook example of how mechanical design features dictate the exact location of metallurgical degradation.
Okay, so we know the underlying physics, we know the fluid dynamics, and we know exactly where these cracks will form. The challenge now falls to the field inspector.
This is where the rubber meets the road.
Exactly. Section 5. In situ inspection and damage detection. The refinery is running, the equipment is covered in decades of operational scale, and you have a potential network of microscopic, oxide-filled grain boundary cracks hiding 1/10 of an inch from a nozzle weld.
Good luck seeing that with the naked eye.
Right. The text is totally clear that visual inspection is entirely inadequate. We have to utilize advanced non-destructive testing, or NDT.
Visual testing cannot resolve intergranular cracking unless the crack has already progressed to a macro-level failure.
At which point the inspection has failed its primary objective.
Right. The API 5701 text authorizes 3 specific electromagnetic NDT techniques for detecting Amine SCC.
Let's list those out.
Sure. Wet fluorescent magnetic particle testing, or WFMT, alternating current field measurement, or ACFM, and eddy current testing, ECT.
Let's start with WFMT. This relies heavily on the physical properties of carbon steel, doesn't it?
It does. Carbon steel is highly ferromagnetic. The inspector uses an electromagnetic yoke to induce a magnetic field into the component.
So the yoke introduces magnetic flux lines that travel smoothly through the continuous atomic lattice of sound carbon steel.
Yes. The inspector then applies a liquid suspension containing extremely fine iron particles that have been coated with a fluorescent dye.
But when those flux lines encounter a crack, the physics change.
Drastically. The crack itself, even though it's filled with iron oxide, has a significantly different magnetic permeability than the base solid steel.
It acts as a region of high magnetic reluctance.
That's the core principle of flux leakage right there. Because the magnetic flux lines cannot easily cross the crack or the oxide fill, they are forced to detour.
They literally leak out of the surface of the metal into the air immediately above the crack.
Exactly. And this concentrated leaking magnetic field acts like a powerful localized magnet. As the liquid suspension flows over the surface, the fluorescent iron particles are instantly pulled out of the suspension.
And they just magnetically lock right over the crack opening.
Yep. When the inspector illuminates the area with an ultraviolet black light, those fluorescent particles fluoresce brightly against the dark background of the steel. It provides an extreme contrast ratio.
A microscopic invisible crack is suddenly highlighted as a glowing, jagged line.
It's an elegant application of physics.
It is. But WFNT has limitations. I mean, it requires messy liquid suspensions, direct surface contact, and it generally only provides information about the length of the crack, not its depth.
Which is exactly why the text brings in ACFM and ECT. Both of these rely on electromagnetic induction rather than gross magnetic flux leakage.
So with ACFM and ECT, we're utilizing the principles of Faraday's law of induction.
Correct. A probe containing an alternating current coil is brought near the surface of the steel. This changing magnetic field induces secondary electrical currents, eddy currents, to flow within the surface layer of the carbon steel.
And because of the skin effect in alternating currents, these eddy currents are highly concentrated right at the surface.
Exactly where Amine SCC initiates.
Right.
So in sound metal, these eddy currents flow in uniform, predictable, circular patterns. But a crack acts as a high-resistance barrier.
So when the eddy currents encounter the crack, they're forced to flow down and around the root of the crack.
Yeah, and this physical detour changes the path length of the current, which in turn alters the secondary magnetic field produced by the eddy currents themselves.
And the probe contains sensor coils that detect these minute changes in the magnetic field. What makes ACFM particularly powerful compared to standard ECT in this specific application?
Well, ACFM was specifically designed to induce a uniform, unidirectional electrical field rather than the circular fields of standard ECT.
Ah, so it's more directed.
Yes. By measuring both the magnetic field component parallel to the crack and the component perpendicular to the crack, complex algorithms within the ACFM software can calculate not just the length of the crack,
But also the depth.
exactly. It provides a highly accurate mathematical estimation of the crack's depth. This allows engineers to conduct fracture mechanics assessments to determine if the vessel is safe to operate or if immediate repair is required.
That's incredibly powerful data. However, all three of these advanced electromagnetic methods share a single critical vulnerability, and the API 571 text emphasizes this heavily.
Oh yeah, surface preparation. It is an absolute imperative.
If an inspector attempts to run a magnetic yoke or an ACFM probe over a weld that is still coated in operational scale, hard rust, or baked on hydrocarbons, the test is compromised.
Honestly, it's worse than compromised. It provides a false negative, which is the most dangerous outcome in asset integrity.
Because it tells you it's safe when it's not.
Right. The magnetic flux leakage or the induced eddy currents simply cannot bridge the gap created by thick, non-conductive, non-magnetic scale. The particles won't gather, or the probe liftoff will be too high to read the impedance changes.
So the text strictly mandates that the surface must be aggressively cleaned.
It does.
And it doesn't just say clean it, it provides the specific, authorized mechanical methods:
Yeah.
grit blasting, high-pressure water blasting, or flapper wheel abrasive grinding.
And we really need to discuss the metallurgy of the cleaning process itself here.
Because the text specifies a flapper wheel, which is made of overlapping flaps of abrasive sandpaper cloth, and implicitly warns against using aggressive hard grinding discs or heavy wire wheels. Why is that?
Because the cleaning process cannot be allowed to alter the mechanical properties of the defect. Carbon steel, while strong, is also relatively ductile and malleable at the microscopic level.
Right. So if an inspector uses a heavy, rigid grinding disc and applies too much pressure to remove the hard scale,
The sheer mechanical force of the disc will peen and smear the surface layer of the steel.
it induces localized plastic deformation.
Precisely. You are plastically flowing the metal right over the mouth of the crack. You essentially caulk the crack shut with a microscopic layer of smeared steel.
And once that crack mouth is bridged by continuous metal,
The magnetic flux lines will no longer leak out of the surface, and the eddy currents will flow smoothly across the smeared bridge without having to detour around the root of the crack.
wow, you have effectively hidden the crack from the NDT instruments. The crack is still there, still propagating under the surface, but the inspector's screen will just show clean metal.
Exactly. A flapper wheel avoids this by providing a flexible, compliant, abrasive surface. It removes the brittle scale and polishes the steel without imparting the massive, localized compressive forces required to smear the ductile base metal.
And grit blasting and high-pressure water blasting achieve the same goal through erosive action rather than heavy grinding.
Right. The text demands surgical cleanliness that preserves the microscopic integrity of the crack mouth.
Okay, we have diagnosed the metallurgy, mapped the process drivers, and detected the microscopic fissures. Now we arrive at Section 6, mitigation and prevention. We need the definitive engineering solution.
How do we fix it?
Exactly.
Yeah.
If a refinery is locked into using carbon steel piping, and the process dictates that amine must flow through it, how do we absolutely immunize the steel against this mechanism?
Well, we must neutralize one of the 3 required factors for stress corrosion cracking. We cannot change the material, and we cannot remove the amine environment.
Therefore, we must eliminate the tensile stress.
Exactly. And the API text mandates a highly controlled thermal process for this, post-weld heat treatment, or PWHT.
Let's detail the thermodynamics of this mitigation. The text dictates that carbon steel welds must be stress relieved in accordance with 2 specific industry standards, ATI 945 and NASC SP0472.
Yes, those are the governing documents.
And the mandatory parameter is a temperature holding range of 1175 degrees Fahrenheit plus or minus 25 degrees. In metric, that is 635 degrees Celsius plus or minus 15 degrees.
That specific temperature is key.
But why 1175 degrees? Why not 1,000 degrees or 1,500 degrees? What is happening to the atomic lattice at exactly 1175 degrees Fahrenheit?
It is a delicate balance of metallurgical creep and phase stability. As we established, the residual stress is a result of the atomic lattice being locked in a state of high tension. To relieve that tension, you have to give the atoms enough thermal energy to increase their mobility. At 1175 degrees Fahrenheit, the yield strength of the carbon steel drops significantly.
So the material enters a state where localized microscopic plastic flow known as creep can occur.
Yes.
So the stretched rubber band analogy comes back. The heat allows the atomic bonds to slip and slide just enough to let go of that locked-in tension, redistributing the stress evenly across the lattice.
Exactly. The localized peak stresses are relaxed. But, and this is crucial, 1175 degrees is specifically chosen because it remains safely below the lower critical temperature of carbon steel, known as the A1 transformation line.
Because if you were to heat the steel to 1350 or 1400 degrees Fahrenheit, the BCC ferritic or pearlitic microstructure would begin to transform into austenite.
Right. And when it cools back down, you've fundamentally altered the mechanical properties of the pipe. You might destroy its tensile strength or induce brittle martensite.
So 1175 degrees is the thermodynamic sweet spot. It provides enough kinetic energy for creep relaxation of the residual stress, but it preserves the fundamental macroscopic strength and microstructure of the carbon steel component.
Exactly. It fixes the stress without ruining the steel.
Now, the text makes a massive point regarding the scope of this requirement. It's not just for the heavy, multi-pass, full-penetration welds joining massive sections of pipe. The text explicitly mandates this heat treatment for repair welds and internal and external attachment welds.
This is where things go wrong in the field all the time.
Let's analyze the physics of an attachment weld, because this is where many facilities suffer catastrophic failures.
An attachment weld is often viewed by maintenance crews as insignificant. Imagine a massive 36-inch diameter lean amine line. It was fabricated in a shop, fully heat-treated in a massive furnace, and it is entirely immune to Amine SCC.
Okay, totally safe.
But then, 5 years later, a contractor needs to run a small half-inch electrical conduit next to it. They use a standard arc welder to attach a tiny 2-inch steel bracket directly onto the outside of the 36-inch amine pipe to support the conduit.
It's a tiny well. It barely penetrates the surface. Why is it so dangerous?
Because of the thermal mass of the 36-inch pipe. When you strike an arc to weld that tiny bracket, you introduce a localized spot of 3,000-degree heat.
Right.
But the massive steel wall of the pipe acts as an infinite heat sink. The moment the arc stops, that tiny weld pool is quenched by the surrounding cold steel at an incredibly rapid cooling rate.
Which creates an extreme state of thermal contraction and potentially forms a hard, brittle microstructure in the HAZ.
Yes, you have just created a hyper-concentrated high residual stress zone on the pressure boundary of an active amine line.
So the physical size of the weld is completely irrelevant to the cracking mechanism.
Completely irrelevant. The localized tensile stress is massive. The amine inside the pipe will find the stress field at the root of that tiny external weld, initiate an intergranular crack, and that crack will propagate completely through the 36-inch wall.
The failure of a massive system driven by a 2-inch bracket.
It happens. This is why the API text is absolute. All repair and attachment welds must undergo PWHT to 1175 degrees.
But practically speaking, you cannot take a 36-inch active pipeline out of the pipe rack and put it in a furnace to heat treat a tiny bracket weld.
No, you have to perform a local PWHT in the field using ceramic heating bands wrapped around the pipe.
And the text provides strict rules for this, referencing NC SP 0472 and WRC 452.
Right. WRC 452 dictates the mathematical modeling of the required heating band width. This is critical to avoid creating new residual stresses.
Let's explore that. If I just wrap a narrow 3-inch heating band directly over the weld and crank it to 1175 degrees, what happens to the steel right at the edge of the heating band?
You create a massive, severe thermal gradient. The steel under the band expands drastically due to the heat, while the steel, just an inch away, remains cold and rigid.
So when the heating band is turned off,
the localized heated zone tries to contract, but the adjacent cold metal fights it. You successfully relax the stress at the weld, but you permanently locked in a massive new ring of tensile residual stress right at the boundary of the heating zone.
you just moved the Amine SCC initiation site an inch to the left.
Exactly. So WRC 452 calculates a wide gradient. The heating bands must extend far enough along the pipe to ensure that the transition from 1175 degrees down to ambient temperature is incredibly smooth and gradual.
It manages the thermal expansion and contraction over a large physical area so that no localized peak stresses are locked into the atomic lattice during the cool-down phase.
It is all about managing the thermal profile to ensure absolute atomic relaxation.
Now, before we conclude, we must address the final operational warning in the text.
No.
This is a trap that catches even experienced maintenance planners.
Oh, the pre-work trap.
Yes. It involves the preparation of the equipment before the welder even arrives to make a repair or apply a heating band. The text emphasizes the strict requirement to thoroughly water wash non-PWHT'd carbon steel piping and equipment prior to welding, prior to heat treatment, or prior to steaming out.
This is a highly critical safety and integrity directive. When amine equipment is drained for maintenance, it is never truly empty.
Right. Microscopic amounts of amine remain trapped in the porous operational scale.
Or in the microscopic crevices of flanges, or in the rough profile of older welds.
So what happens to that trapped residual amine if a maintenance crew skips the extensive water wash and immediately applies 1175-degree ceramic heating band, or injects 400-degree high-pressure steam to clear the line?
You fundamentally alter the kinetics of the cracking mechanism.
How so?
Well, amine stress corrosion cracking is typically a time-dependent mechanism that takes months or years to propagate under normal operational temperatures. However, when you apply severe external heat to trapped liquid amine, you drastically spike its vapor pressure and force it into rapid boiling.
You supercharge the chemistry.
You do. The aggressive boiling action concentrates the corrosive constituents of the amine in the microscopic crevices. The extreme heat accelerates the anodic dissolution reactions at the grain boundaries exponentially.
And simultaneously, the application of the heat creates temporary massive thermal stresses as the pipe expands.
Exactly. You are combining an aggressively accelerated chemical attack with immediate high thermal stress.
It's the perfect recipe for instantaneous failure.
You basically compress years of stress corrosion, cracking into a matter of minutes or hours. The pipe will rapidly unzip itself under the heating bands, or during the steam-out process.
That is terrifying. So what's the fix?
The only mitigation is mechanical dilution. The equipment must be meticulously water-washed, circulating massive volumes of clean water to physically flush every single molecule of residual AN out of the scale and crevices before any thermal energy is introduced to the steel.
It's a profound reminder that we are dealing with systems that are incredibly sensitive to both mechanical history and chemical state. The intersection of thermodynamics, metallurgy, and operational flow is truly unforgiving.
But, it is entirely manageable when you rigorously adhere to the engineering controls, the strict PWHT parameters, and the advanced NDT inspection protocols dictated by the standard.
And I want to leave you, the listener, with a final thought to mull over regarding the nature of this threat. We learned today that Amine SCC doesn't care how thick your vessel walls are, and it doesn't attack faster just because the amine is highly concentrated.
Right, it's driven by that invisible tension.
Yes, the invisible tension locked within the atomic lattice and the subtle phase transitions of the fluid. So, look around your facility. Consider the hundreds of miles of piping. How many seemingly safe, robust systems operating at low amine concentrations might be sitting on the absolute edge of fracture simply because a tiny, undocumented attachment weld made 20 years ago skipped that critical 1175-degree relaxation bake?
It really is the invisible history of the metal that dictates the future of your asset.
That wraps up our technical deep dive on this mechanism. Don't leave your exam or your asset integrity to chance. Head over to megintegrity.ca right now to subscribe to our full premium library, download the Visual Slide Companion Pack, and master API 5721. Until next time, keep your assets safe and your inspections rigorous.